talk about more circles. This is section 10.4, which deals with inscribed angles and polygons. And we're going to start by going back 2 sections. We talked about central angles, which are angles that have the vertex at the center, and it creates minor arc AB and the major arc around the other direction. I don't have another point, but ADB, if you would. We talked about that the arc AB, the measure of that arc is equal to the measure of the angle. So if this was 80 degrees, the measure of arc AB would also be 80 degrees as a review. But we're talking about today inscribed angles. So I'm going to draw an inscribed angle by drawing 2 rays. I'm just going to pick a point here, one that goes through, starts on the circle and goes through a point here. I'm trying to create that same arc AB. There we go. So I draw 2 rays. We're going to go ahead and call this point D, where it touches the circle. And the chords of this angle, chord DA and DB, I'm going to darken those a little bit, create what we call an inscribed angle. There we go. So we're really only talking about the part of those 2 rays that is inside the circle. We would call this angle D, and we have 2 chords, DA and DB. So this is called an inscribed angle, okay? Angle D, or we might say angle ADB, either way. There's no other angles at D, so we could just call it angle D. And inscribed angles intercept or create a minor arc, and you kind of say a major arc, even though it touches it here. This is the arc on the outside, but we're really more looking at the minor arc here. Angle D is also creating arc AB, and this time we say when an inscribed angle creates that arc, we call that the intercepted arc, and that one is arc AB. Now if you notice, we know that arc AB is still named by that central arc that first creates it, or that it comes from. But notice that this arc, or this angle that is intercepting AB, is smaller than the central angle. And that's going to give us a theorem here. So this still, if this is 80 degrees, my arc is still 80 degrees, but notice that this angle back here is less than, and it's actually going to be 1/2 of the measure of AB. So this angle is actually 40 degrees. That's going to be our first theorem. Let's take a look at it. Okay, let's look at theorem 10.7. I'm getting a lot of theorems here, so hopefully you have started your notebook already. I may have said that last time. Theorem 10.7, the measure of an inscribed angle is half the measure of the intercepted arc. Okay, so let's look at our picture here for an example. We actually have 2 inscribed angles. Hopefully you see it. Angle D, or EDB, and angle B, or ABD. They're both inscribed angles, and they both intercept an arc. Angle D intercepts arc EB. Angle B intercepts arc AD. Now by our theorem, we know that the angle measure is half the measure of the arc. So we're going to find all our parts, and hopefully it is straightforward up to a point. Okay, now A here says find the measure of angle D. Well, we know angle D intercepts arc EB. EB is 100 degrees. That means our measure of angle D is going to be 50 degrees. Okay, now it's going to work backwards as well. This time we're finding arc AD. Well, we know arc AD is created by inscribed angle B here. So if B is 35, we're going to go the other direction. That means our arc has to be 70 degrees. It's going to be double what the angle is. Kind of backwards from what that says. Now the last one here is a little tricky, so take a look at it. They're asking us to find arc AB. This arc is here. This one is not created by any angle. It's not an intercepted arc, but by what they give us, we should be able to find it. So what I want you to notice, what they don't always mark is the diameter. So do you guys remember the diameter creates two arcs that are both semicircles, both 180 degrees. So look for those in your picture because they're not going to mark them for you half the time. All right, so DB, chord DB here is a semicircle. So we know that the arc DAB is 180 degrees. So in order to find AB, we can subtract arc AD, which we just found. So we're going to find measure of arc AB, we take 180 degrees minus our 70. So arc AB is left at 110 degrees, okay? So I wanted to do one of those to make sure you look for the semicircles in there. Now watch your definitions, your terms here. Inscribed angles are the angles that have a vertex on the circle and the endpoints are on the circle. So that's inscribed angle D, and the arc it creates is the intercepted arc. Let's look at one more example using our theorem 10.7. We have a circle, and notice we have a bunch of different inscribed angles. So here's the first part. If the measure of angle L, right here, is 52 degrees, find the measure of arc KN, which is right here, and the measure of angle KMN, which is this angle here, okay? So we learned in our last theorem that the arc that is intercepted by the inscribed angle is twice the angle measure. So we know if this angle is 52, that means that KN is going to be 104 degrees. Let's say here that's 104 degrees. And then they want us to go find the measure of angle KMN. Well, if you look at that, this angle inscribes KN as well. So that means the measure of angle M here is half the measure of our arc, which is 52 degrees. So you'll notice that these two angles intercept the same arc, so they have to equal the same degree measure, 52. So when they ask you here, what do you notice about angle L and angle M, we can say that they are congruent. Angle L is congruent to angle M. All right? Now then that part says, can you name two more congruent angles, two more of these? Hopefully you see that there is angle K here and angle N, and they also both intercept the arc at arc LM. Now we don't know what the angle measure or the arc measure is, but we can actually say, without knowing the measure, that angle K is also congruent to angle N. So watch that in your pictures. Sometimes you're going to have more than one inscribed angle intercepting an arc, but you know they're going to be congruent. Okay? Watch out for those. Okay, our last example gives us this theorem, theorem 10.8. If two inscribed angles intercept the same arc, then they are congruent. And again, that comes from the theorem before that, because we know that this angle B here inscribes arc CD, so it's half the measure of that. And so similarly, angle A inscribes the measure of arc CD, so it is also half of the measure. Since they are equal, they must be congruent. That's where it comes from. So we can say from this picture, we know that angle A is congruent to angle B, and angle C is congruent to angle D, because again, C and D also intercept arc AB. Here's your first question. Remember to write down the answer for me. Turn it in. The question is, what is the minor arc called that is created by an inscribed angle? What do we call that minor arc? Question 1. All right, let's take a look at our next section, which is talking about inscribed polygons. Okay, so these are polygons that every vertex lies on the circle. Okay, so that's what you're looking for, inscribed polygons. We talked about these a couple chapters back when we were dealing with our incenters and our circumcenters, and we had inscribed circles and circumscribed circles. So those words are coming back, but I want you to take a look at them in this case here. So an inscribed polygon is when our polygon is inside our circle. So we would call this an inscribed quadrilateral. This is an inscribed triangle. But we would say that the circle circumscribes the figure. So we would say this is a circumscribed circle, the inscribed quadrilateral. That means it's on the outside. This is the circumscribed circle, inscribed triangle. I just want to point those out because they'll use those words in your examples or in your problems. Okay, so let's look at, there's two special kinds of inscribed polygons we want to take a look at. All right, let's take a look at our first special inscribed polygon, the right triangle. Okay, now I drew the right triangle. If you look at it, the hypotenuse happens to be, and maybe it happens to be, but maybe it is a special reason, happens to be the diameter of our circle. Okay, now actually I drew this triangle by first drawing the diameter, okay, and then I picked a point and I drew the lines to it. Now see if this makes sense. Why does that have to be a right angle when I make sure that the first line is the hypotenuse? Now remember, the diameter creates two arcs, arc BC and arc CB going the other way, CAB. And we know that the semicircle always creates a 180-degree arc. Our last theorems talked about inscribed angles, and how the inscribed angle is always half the measure of the arc that it intercepts. So if arc A here actually is an inscribed angle, if you look at it that way, arc A, or angle A inscribes or intercepts arc BC, which is 180 degrees. So that means that angle A must be 90 degrees, must be a right angle, and therefore it must be a right triangle. So that gives us the next theorem, and we're going to write it out. Hang in there. Added the theorem to our picture here. It's kind of long, and I don't really know why they didn't write it, kind of fashion it as a biconditional, but it does list the statement and its converse separately, but let's read it. So it says, if a right triangle is inscribed in a circle, such as we have here, then the hypotenuse is a diameter. Conversely, if one side of an inscribed triangle is a diameter, then we know the triangle is a right triangle. So it does have the statement and the converse. I don't know why they didn't write it together, but there it is. Okay, hopefully that one makes sense. Anytime you see that diameter, you make a triangle from there, it has to be 90 because that arc is 180 degrees, okay? Vice versa, whenever you see that right triangle, you know you're going to wind up with a diameter even though they don't mark it. So watch that. Okay, let's look at our second special inscribed polygon, and it is inscribed quadrilaterals. Now, not every quadrilateral can be inscribed in a circle. There's a special condition. And it happens to be that the opposite angles must add up to 180 degrees. Now, my hope is that I could show you why this is true and that it'll make sense to you. Okay, so let's look at what this says is that my opposite angles, such as A and C, they're saying that angle A plus angle C has to equal 180 degrees, and angle B plus angle D must add up to 180 degrees. Now what I'm hoping is that you'll see that, looking again at our theorems we just talked about, A is an inscribed angle. Can you see that here? So from BAD, this angle inscribes this arc right here, okay? And we don't know what it equals, but angle A is half of whatever that arc measure is, okay? Let's grab another color. Now angle C, the other one that has to add to 180, angle C inscribes the arc BAD. Now angle C is going to be half the measure of arc BAD. Again, we don't know how much it is, but we know that it's half. Together, the orange arc and the pink arc add up to 360 degrees because it covers the entire circle. So therefore, A plus C, which equals half of that, have to add up to 180 degrees. Hopefully that kind of makes sense. Same thing here with B and D. Angle B inscribes arc ADC, and angle D here intercepts arc CBA. Again, we cover the whole circle, so B plus D, which is half the circle, has to add up to 180 degrees. So let's write out our theorem. All right, let's read theorem 1010 together. Same picture, and it's basically what we just said, but in our nice little math language. A quadrilateral can be inscribed in a circle if and only if the opposite angles are supplementary. So again, has to be both pairs, B and D have to add up to 180. A plus C must also add up to 180. Let's look at a couple examples using this theorem. All right, here's our first example. We have our quadrilateral inscribed in our circle. They're asking us to find X and Y. Okay, now you may recall when you see these, oh, I know quadrilateral adds up to 360 degrees, but don't let that throw you off, because once it's inscribed in a circle, we're going to focus mostly on the fact that the opposite angles have to add up to 180 degrees. Okay, so that's what we want to set up here. Set up our two equations. X plus 82 equals 180 degrees. So we're going to subtract that, so we know that X has to equal 98 degrees. And then opposite this time, Y plus 68 is going to equal 180 degrees. So we subtract 68 from this side, we know that Y equals 112 degrees. Okay, kind of straightforward, but don't let it mess you up. I also want to point out to watch, because each one of these angles is also an inscribed angle. For example, angle D does intercept arc CBA, and angle A intercepts arc BCD. So we're going to look at one where you might have to pull the arcs and the angles together. Hang in there. Okay, we paused for our second question of the day, which is, when can a quadrilateral be inscribed in a circle? So you're telling me how I can tell a quadrilateral can be inscribed in a circle. Let's take a look at our last example. We again have an inscribed quadrilateral in our circle, and we're looking for the values of our variables, X and Y. Now, again, we can't just add everything up because we have two different variables. But we do know, again, that an inscribed quadrilateral, the opposite angles equal 180 degrees. So what we want to do to find X is say angle A plus angle C equals 180, but we don't know what angle A is. So now we need to change our focus here and say, okay, well, angle A is also an inscribed angle, and it intercepts arc BCD. And if we know arc BCD, then we know that our angle is half of the measure of that arc. So let's look at what we have here. BC is equal to 152 degrees. DC is equal to 80 degrees. So we know that the measure of arc BCD is equal to 152 degrees plus 80 degrees, which gives us 232 degrees for the measure of arc BCD. And again, we know angle A has to be half that measure. So the measure of angle A then is going to be 116 degrees. Let's go ahead and write that in here. So now we can set up our equation. We know angle A plus angle C equals 180 degrees. So we're going to set up 4x plus 116 equals 180. Please do not set them equal. People will do that, but that's not our equation. We know they have to add up to 180 degrees. So the first thing we do is subtract 116. So we wind up with 4x equals 64 degrees. And the last thing, divide by 4. So x equals 16. All right, so we have our answer, x equals 16. Now we can concentrate on y. We know that angle D plus angle B must add up to 180 degrees. Again, we don't know angle B, but they do give us the arc measures. Angle B is an inscribed angle. It intercepts arc ADC. And they happen to give us the measure of arc AD, the measure of arc DC. So the measure Got right over here, of arc ABC equals 84 plus 80 degrees, which is 164 degrees. All right, so that means that angle B is going to be half of that. The measure of angle B is 1/2 of 164 degrees, which is 82 degrees. Let's make a degree sign, not a square sign. Okay, 82 degrees. Let's go ahead and write that in here. That's 82 degrees. We can set this equal there. So 7y plus 82 is going to equal 180. You will be tempted again to set it equal, but don't do it. Okay, so we're going to subtract 82 from both sides. We wind up with 7y equals 98 degrees. And we divide this by 7. If I can fit this in here, that goes in there 14 times. And y equals 14 degrees. We are done. So just be careful. Sometimes you have to deal with it as the quadrilateral, adding up the angles to equal 180, and sometimes you have to think of them as inscribed angles with intercepted arcs. Okay, so keep an eye out for those. All right, we're back. That finishes up our section 10.4 on inscribed angles and inscribed quadrilaterals. This is also the last video for this week. You've had a lot this week, four sections, so let me know how you're doing. Hopefully everything's catching on, you're working good with your homework. Remember, we're going to have a quiz on Friday on sections 1 through 4, so if you have any questions, we'll talk Friday morning. Just make sure you're ready for that, okay? Now we are ready for our joke of the day. How do you keep warm in a cold room? The answer is, you go to the corner, because it's always 90 degrees. All right, have a good day and do good on your work. See you soon.